March 20th, 1944. Kaufering airfield, Bavaria, Germany. The Packard-built Rolls-Royce Merlin engine coughed once, twice, then fell silent. Second Lieutenant Charles Bailey of the 354th Fighter Squadron, 355th Fighter Group, had been nursing damaged fuel lines for the past 20 minutes, watching his gauges drop while trying to coax his wounded fighter back toward Allied territory. The decision made itself. Below stretched a grass airfield that looked operational, and with no power and rapidly decreasing altitude, Bailey had no choice but to commit to landing. The sleek North American P-51B Mustang, serial number 43-6877, touched down smoothly on German soil. As the aircraft rolled to a stop and Bailey opened his canopy, he saw German ground crew already running toward him, rifles at the ready. Within minutes, he was surrounded. His war as a fighter pilot had ended, but for German engineers, an education was about to begin that would fundamentally challenge everything they believed about fighter aircraft design. Before we jump back in, tell us where you're tuning in from, and if this story touches you, make sure you're subscribed because tomorrow I've saved something extra special for you. What the Luftwaffe discovered when they examined this captured Mustang would shatter their assumptions about what made an effective fighter aircraft. The P-51 represented a radical departure from conventional fighter design philosophy, combining an American airframe with a British engine in ways that created performance characteristics unlike anything German engineers had encountered. Over the following months, as test pilots flew captured Mustangs, and engineers measured every aspect of their design, a troubling picture emerged. Germany hadn't simply fallen behind in one area of fighter development. They had been pursuing an entirely different design philosophy, one that emphasized specific performance parameters, while the Americans and British had discovered how to optimize the complete package. The story of captured Mustangs in German hands reveals how revolutionary thinking in aircraft design, supported by international collaboration and unbounded by traditional assumptions, could produce a fighter that excelled in virtually every category simultaneously. The Mustang would teach German engineers that their understanding of aerodynamic efficiency had been fundamentally incomplete. The capture of Charles Bailey's Mustang wasn't the first time German forces had encountered the P-51 in combat, but it provided the first opportunity to examine an intact, relatively undamaged example of the fighter that was rapidly changing the character of the air war over Europe. By early 1944, Luftwaffe pilots had already filed combat reports describing an American fighter with performance characteristics that seemed almost contradictory. It was fast at all altitudes, not just high altitude like the P-47 Thunderbolt. It could turn with German fighters despite being larger than the Messerschmitt Bf 109. It possessed range that allowed it to escort bombers to targets deep inside Germany, something no other Allied fighter could accomplish. Most troublingly for German pilots, the Mustang seemed to have no significant weaknesses they could exploit. Every other Allied fighter had clear vulnerabilities that experienced Luftwaffe pilots had learned to attack. The P-47 was sluggish below 15,000 feet. The Supermarine Spitfire had limited range and struggled at very high altitudes. The P-38 Lightning could be outmaneuvered in turning combat, but the Mustang performed well in every flight regime, at every altitude, in every type of combat engagement. Initial German intelligence reports struggled to explain this aircraft. Early assessments suggested it might be a modified version of an existing design, perhaps a P-40 Warhawk with a more powerful engine. Some analysts theorized it represented a completely new aircraft designed specifically for the bomber escort role. A few reports speculated that the Americans had finally designed a fighter that prioritized performance over ruggedness and ease of production. All these assessments would prove incorrect. The truth was both simpler and more revolutionary than German analysts imagined. The North American P-51 Mustang represented what happened when designers freed themselves from conventional assumptions about fighter aircraft requirements and pursued optimal performance through ruthless attention to aerodynamic efficiency. The aircraft had been designed around a single revolutionary concept: minimize drag in every possible way, then install sufficient power to overcome whatever drag remained. When Bailey's captured Mustang arrived at Rechlin, the Luftwaffe's primary testing facility located northwest of Berlin, it was immediately assigned to the highest priority evaluation program. Hans-Werner Lersch, the legendary Rechlin test pilot who had evaluated the captured P-47 Thunderbolt months earlier, was again assigned as principal test pilot. Lersch approached the Mustang with the same methodical professionalism he brought to every evaluation, but his initial impressions, later documented in his memoirs, revealed genuine surprise at what he found. The Mustang's cockpit seemed almost minimalist compared to the P-47's complexity. Controls were logically arranged and intuitively placed. Visibility was outstanding, with a bubble canopy providing unobstructed views in nearly every direction. The aircraft felt smaller and lighter than the Thunderbolt, more like a sports car than the heavy truck impression the P-47 had given. But the real revelation came when Lerche began examining the airframe itself with an engineer's eye. Every surface, every curve, every junction between components had been designed with fanatical attention to aerodynamic cleanliness. The wing was extraordinarily thin, far thinner than any German fighter wing. The fuselage was remarkably smooth, with flush riveting throughout and panel gaps minimized to the point where they were barely visible. The engine cowling integrated seamlessly with the fuselage, creating a continuous aerodynamic form. The radiator installation, typically a source of significant drag on liquid-cooled fighters, was positioned beneath the fuselage in a carefully designed duct that not only minimized drag, but actually produced a small amount of thrust through clever use of the heated air passing through the cooling system. German engineers studying the aircraft recognized this immediately as a practical implementation of the Meredith effect, a theoretical concept they understood but had never successfully implemented in production aircraft. The entire aircraft represented a level of attention to drag reduction that bordered on obsessive. Preparing and narrating this story took us a lot of time, so if you are enjoying it, subscribe to our channel. It means a lot to us. Now, back to the story. Lerche's first flight in the captured Mustang took place on a clear morning in April 1944. The Packard-built Rolls-Royce Merlin V1653 engine started smoothly, settling into the distinctive sound that British and American pilots knew well, but that was utterly foreign to German ears accustomed to the harsh mechanical sounds of Daimler-Benz and Junkers inline engines. The Merlin's exhaust note was smoother, almost musical, a sound that spoke of precision engineering and meticulous manufacturing quality. As Lerche advanced the throttle for takeoff, the first surprise arrived. The Mustang accelerated rapidly, much faster than the P-47 had, despite having less engine power. The takeoff roll was short, and the aircraft leapt into the air with an eagerness that immediately communicated responsive flying characteristics. Lerche climbed away from Rechlin, watching his instruments carefully and feeling the aircraft's responses through the controls. At low altitude, the Mustang's handling was crisp and precise. Control forces were light but not overly sensitive, providing excellent feedback without requiring excessive pilot input. The aircraft felt balanced, with no tendency toward heavy controls in any axis. Lerche rolled into a gentle turn, feeling how the Mustang responded. The turn rate was good, noticeably better than the P-47 and comparable to the Focke-Wulf TEMW-190 at this altitude. But it was the quality of the handling that impressed him most. The controls remained light and responsive throughout the turn, with no tendency towards sluggishness or excessive sensitivity. The aircraft simply did what the pilot asked, immediately and predictably. As he climbed through 10,000 feet, Lerche noted that the Mustang's rate of climb was excellent, better than most German fighters at equivalent weights. The Merlin engine maintained power smoothly as altitude increased, and the thin wing continued providing efficient lift. At 15,000 feet, where the P-47 had still felt heavy and ponderous, the Mustang felt light and responsive, its handling characteristics unchanged from low-altitude performance. At 20,000 feet, Lerche began to understand why German pilots had filed such troubling combat reports about this aircraft. The Mustang's performance hadn't degraded at all with altitude. If anything, it felt even more responsive. The controls still light, the acceleration still strong, the climb rate still impressive. He advanced the throttle to maximum continuous power and watched the airspeed indicator climb steadily. The Mustang accelerated smoothly through 350 miles per hour, then 375, then 400, the speed still building with no sign of the aircraft, approaching any performance limit. At 25,000 feet, Lerche leveled off and conducted a series of test maneuvers. He rolled the aircraft through a series of banks, checking roll rate and control response. The Mustang rolled crisply, not quite as fast as the TW-190's excellent roll rate, but faster than the Bf-109 and with lighter control forces than either German fighter. He pulled into a sustained turn, loading the aircraft up to 4 Gs and watching how it responded. The turn rate was excellent, comparable to German fighters at this altitude despite the Mustang being significantly faster. Most importantly, the aircraft remained fully controllable throughout the maneuver, with no tendency toward stalling or spinning. Lerche then conducted the test that German pilots most feared when facing Mustangs in combat. He rolled inverted and pulled into a steep dive, accelerating rapidly toward terminal velocity. The Mustang dove like a stone, accelerating past 450 miles per hour, then 475, then 500. At this speed, most German fighters became almost uncontrollable, their control surfaces stiffening dramatically as aerodynamic forces compressed around the airframe. The Bf-109 developed severe nose-down trim that required enormous stick force to overcome. The full 190's controls became so heavy that recovery from high-speed dives required both hands on the stick and all the pilot's strength. But the Mustang's controls, while certainly heavier at these extreme speeds, remained usable. Lerche could still maneuver the aircraft, still control his flight path, still execute tactical movements. Recovery from the dive required firm pressure on the stick, but was well within the capability of an average pilot. This characteristic alone explained why German pilots reported that Mustangs could escape virtually any engagement simply by diving away at speeds German fighters couldn't safely match. After landing from his first evaluation flight, Lerche's preliminary report contained observations that troubled Luftwaffe headquarters staff even more than his P-47 evaluation had. The Mustang wasn't superior in just one flight regime or at one altitude band. It was superior everywhere. At low altitude, it matched or exceeded German fighter performance in most categories. At medium altitude, it held clear advantages. At high altitude, it dominated completely. The aircraft had no significant weaknesses that German pilots could exploit tactically. An experienced pilot in a well-flown Bf-109 or F-190 might achieve temporary advantage in specific situations, but the Mustang pilot always had the option to disengage, and there was nothing German fighters could do to prevent it. The captured Mustang underwent the same exhaustive technical evaluation that every captured aircraft received at Rechlin. Teams of engineers photographed every component, measured every dimension, weighed every part, and tested every system. What they discovered was a masterclass in aerodynamic optimization that challenged fundamental assumptions about fighter design that had guided German engineering for years. The wing design represented the most radical departure from conventional practice. German fighters used relatively thick wings, typically with thickness-to-chord ratios between 14 and 16%. These thick wings provided structural strength, adequate internal volume for fuel and armament, and good low-speed handling characteristics. They also generated significant drag, especially at high speeds, where the thick airfoil profile created strong shock waves as the aircraft approached the speed of sound. The Mustang's wing used a laminar flow airfoil with a thickness-to-chord ratio of just 11.4% at the root, thinning to approximately 10% at the tip. This radical thinness created enormous engineering challenges. The wing had to be strong enough to handle combat loads, while being too thin to accommodate conventional structural approaches. North American aviation's engineers had solved this problem through innovative structural design that placed the main spar farther aft than conventional practice, allowing the forward portion of the wing to maintain its precise aerodynamic shape, while the rear portion handled structural loads. The payoff for this complexity was dramatic drag reduction at high speeds. The thin laminar flow airfoil delayed the formation of shock waves that plagued conventional wings at speeds approaching Mach 0.7. This allowed the Mustang to maintain efficient flight at speeds where German fighters encountered compressibility effects that limited their performance. German engineers examining the wing structure recognized immediately that they were looking at manufacturing precision that exceeded standard German production capabilities. The wing skin was remarkably thin, requiring exact forming to maintain the precise airfoil shape that made the laminar flow concept work. Any waviness or irregularity in the skin would disrupt the smooth airflow that was essential to the design's effectiveness. The flush riveting throughout the wing wasn't simply cosmetic or even just about drag reduction. It was structurally necessary to maintain the precise surface contours that the laminar airfoil required. Achieving this level of precision in mass production represented a manufacturing challenge that German industry, already struggling with material shortages and the degradation of quality control as skilled workers were replaced with forced labor, could not hope to match in 1944. The engine installation revealed another dimension of the Mustang's sophisticated design philosophy. The Packard V 1653, a license-built version of the Rolls-Royce Merlin 61, was mounted in a carefully designed cowling that minimized frontal area while providing adequate cooling airflow. The liquid cooling system used ethylene glycol coolant circulated through radiators positioned in a ventral duct beneath the fuselage. This duct was designed according to principles that German engineers understood theoretically but had never successfully implemented in practice. Air entered through an intake carefully sized and positioned to minimize drag. As the air passed through the radiator matrix, it absorbed heat from the cooling system. The heated air then expanded, and the duct was designed so that this expansion accelerated the air, creating a small amount of thrust that partially offset the drag of the radiator installation. In ideal conditions, the installation could actually produce net thrust, meaning the cooling system added speed rather than subtracting it. German engineers had attempted similar installations on experimental aircraft, but had never achieved the manufacturing precision and design optimization necessary to make the concept work reliably in production fighters. The engine itself represented collaboration between American manufacturing capability and British engineering excellence that produced results neither nation might have achieved alone. Rolls-Royce had developed the Merlin as a sophisticated high-performance engine using advanced metallurgy and precision manufacturing. Packard had taken the British design and adapted it for American mass production methods, implementing manufacturing processes that allowed production of the complex engine in quantities that Rolls-Royce's more traditional methods couldn't match. The result was an engine that combined British engineering sophistication with American production efficiency. By 1944, Packard was producing Merlin engines at a rate exceeding 2,000 units per month, more than Germany's total production of all fighter engines combined. The V1653 variant installed in the Mustang incorporated a two-stage, two-speed supercharger that maintained engine power to altitudes exceeding 30,000 feet. This supercharger system was mechanically more complex than the turbo supercharger system used in the P-47, but it was also lighter, more compact, and required less maintenance. German engineers examining the engine noted the quality of materials throughout. Cylinder heads were precisely cast and carefully machined. Valve gear incorporated hardened components that showed no wear despite hours of operation. The supercharger impellers were balanced to extremely tight tolerances, allowing them to spin at high speeds without vibration. Every component showed evidence of precision manufacturing to specifications that German industry could no longer consistently achieve. The armament installation demonstrated American preference for overwhelming firepower delivered through reliable weapons systems. The P-51B model carried 4 Browning M250 caliber machine guns, 2 in each wing, with 350 rounds per gun. Later, P-51D models would increase this to 6 guns with 400 rounds per gun in the center positions and 270 rounds for the outer positions. While this represented less total firepower than the P-47's 8 guns, the Mustang's installation was more efficient. The guns were positioned closer to the fuselage, where structural strength was greatest and where harmonization was simpler to maintain. Ammunition boxes were designed for easy reloading by ground crew, The installation included electric heating to prevent freezing at altitude, and spent cartridge cases were ejected cleanly without fouling control surfaces. Testing of the armament system revealed the same attention to reliability that characterized every aspect of the aircraft. The guns fired without jamming through thousands of rounds. The ammunition was consistently manufactured to specifications that ensured reliable feeding and ignition. The German test. Pilots who flew the captured Mustang after Lerche's initial evaluation consistently reported the same fundamental observation. This aircraft didn't excel through brute force or overwhelming power. It succeeded through efficiency, through doing everything slightly better than necessary, through attention to countless small details that individually seemed insignificant but collectively produced revolutionary results. The Mustang cruised faster than German fighters flew at maximum speed. It climbed better, dove better, turned adequately, and possessed range that transformed strategic bombing from a costly gamble into a sustainable campaign. Most frustratingly for German engineers analyzing the design, there was no single technological breakthrough they could point to and say this is what makes it superior. The Mustang's excellence emerged from systematic optimization of every element of the design, supported by manufacturing quality that maintained precise tolerances throughout production. German engineering reports compiled at Rechlin emphasized this point repeatedly. The Americans and British hadn't invented fundamentally new technology. They had taken existing concepts, refined them relentlessly, and implemented them with manufacturing precision that Germany could observe and measure but no longer replicate. The laminar flow wing was theoretically understood in German aerodynamic circles, but building wings to the tolerances required for laminar flow to work in practice exceeded German manufacturing capabilities. The Meredith effect radiator installation was documented in German technical literature, but implementing it successfully required precision in duct design and manufacturing that German factories couldn't consistently achieve. The two-stage supercharger was conceptually similar to German experimental systems, but building it reliably in quantity production required quality control and material consistency that German industry had lost as strategic bombing damaged factories and skilled workers became scarce. The performance testing at Rechlin produced data that quantified exactly how superior the Mustang was across the entire flight envelope. At sea level, the P-51B achieved maximum speed of approximately 370 miles per hour. The Foot W-190A8 managed approximately 408 miles per hour at the same altitude, giving the German fighter clear advantage in low-altitude combat. But at 10,000 feet, the Mustang reached 390 miles per hour, while the Focke-Wulf achieved approximately 395 miles per hour. The gap was closing. At 20,000 feet, the Mustang hit 420 miles per hour, while the Falev 190 managed approximately 380 miles per hour. At 25,000 feet, where much of the air combat over Germany now occurred as bomber formations sought altitude to escape anti-aircraft fire, the Mustang reached 440 miles per hour. The Forlar 190 struggled to reach 370 miles per hour, and its performance was degrading rapidly as altitude increased. The Bf-109 G6 achieved approximately 385 miles per hour at 25,000 feet, better than the Focke-Wulf, but still significantly slower than the Mustang. At 30,000 feet, the performance gap became a chasm. The Mustang maintained 430 miles per hour. German fighters were operating at the edge of their performance envelope, their engines gasping for oxygen, their controls sluggish, their pilots struggling to maintain formation. Combat at these altitudes decisively favored the Mustang, and increasingly, combat occurred at these altitudes because that's where American bomber formations operated. The climb rate comparison proved equally disconcerting for German analysts. The Mustang climbed to 20,000 feet in approximately 7 minutes. The 4W190 required approximately 8.5 minutes. The Bf-109 G6 managed approximately 7.5 minutes. These differences might seem minor, but in combat situations, that minute or two of difference determined whether German interceptors reached bomber altitude before the formations struck their targets or arrived too late to effectively engage. More significantly, the Mustang escorts could climb with the bombers, maintaining position throughout the mission profile, while German fighters had to climb from ground level after bombers were detected, always playing catch-up, always arriving at combat altitude with less fuel and less energy than the American escorts who had been cruising efficiently at altitude for hours. The range comparison revealed the strategic transformation the Mustang represented. With internal fuel only, the P-51B could fly approximately 950 miles, enough for round-trip missions penetrating several hundred miles into German territory. With external drop tanks, the combat radius extended to approximately 750 miles, allowing escort of bomber formations to targets anywhere in Germany and significant portions of occupied Eastern Europe. German fighters designed for short-range interception missions defending the Reich had combat radius measured in hundreds of miles at most. The Bf-109 G6 with external tank managed perhaps 400 miles combat radius. The Fuller 190 was similar. This fundamental difference in operational radius meant American fighters could choose when and where to fight. German fighters had to engage near their bases because they lacked fuel for extended operations. If American formations bypassed certain areas, German fighters based there were irrelevant to that day's combat, regardless of how many aircraft were available. The handling characteristics testing revealed subtleties that explained why experienced pilots praised the Mustang so enthusiastically. The aircraft wasn't necessarily superior to German fighters in raw maneuverability measurements. The Bf-109 could outturn it in sustained combat at medium altitudes if both aircraft started with similar energy states. The Fuhr W190 had slightly better roll rate at low speeds, but the Mustang's handling was more linear, more predictable, more forgiving across the entire flight envelope. German fighters had distinct characteristics at different speeds and altitudes. The Bf-109 required careful attention to rudder trim as speed changed. The W190's control forces varied significantly between flight regimes. Pilots had to know these characteristics intimately and compensate constantly. The Mustang simply responded consistently. Controls that felt good at 200 miles per hour felt similar at 400 miles per hour, just heavier due to aerodynamic forces. The aircraft that turned predictably at 10,000 feet turned predictably at 30,000 feet. This consistency reduced pilot workload and allowed pilots to focus on tactics and situational awareness rather than aircraft management. German test pilots noted another crucial characteristic. The Mustang was genuinely difficult to stall or spin accidentally. German fighters, particularly the Bf-109, required careful handling near the edges of the flight envelope. Pull too hard in a turn, and the wing could stall abruptly, potentially entering a spin that required altitude and skill to recover from. The Mustang provided clear warning before stalling, gave the pilot time to reduce angle of attack, and recovered quickly when stalled. This forgiving nature meant average pilots could fly the Mustang near its limits with reasonable safety, while flying a Bf-109 near its limits demanded experience and skill. In combat, where pilots were constantly pushing their aircraft to maximum performance, this difference in handling characteristics translated directly into survivability. Inexperienced American pilots could survive mistakes that would kill inexperienced German pilots in less forgiving aircraft. The engineering team at Rechlin paid particular attention to the fuel system, recognizing that the Mustang's extraordinary range had to be enabled by something beyond simply carrying more fuel. What they discovered was a fuel management system designed with the same attention to efficiency that characterized every aspect of the aircraft. Internal fuel tanks were positioned throughout the fuselage, carefully arranged to maintain proper center of gravity as fuel was consumed. The main tank sat behind the pilot, a position that initially seemed dangerous in combat but actually provided excellent protection because the pilot's armor plating was between the tank and the most likely direction of enemy fire. Forward fuselage tanks were smaller and used first, ensuring the aircraft maintained proper balance throughout the mission. External, drop tanks could be carried on underwing pylons, typically two 108-gallon tanks for maximum range missions. These tanks were jettisoned when empty or when combat was imminent, reducing drag and weight before engagement. The fuel system included automatic tank switching and sophisticated plumbing that ensured engines received fuel reliably, regardless of attitude or G-loads during combat maneuvering. German fighters used simpler fuel systems that sometimes caused engines to cut out during negative G maneuvers, a characteristic British and American pilots had learned to exploit tactically by pushing into sudden dives that German fighters initially couldn't follow. The Mustang's fuel injection system maintained engine power regardless of aircraft attitude, eliminating a tactical vulnerability that German fighters had never fully overcome. The quality of construction throughout the airframe impressed German inspectors who examined every detail of the captured aircraft. The aluminum alloy used for primary structure was consistently high quality, with no evidence of material substitution or inferior alternatives being employed due to shortages. Riveting was precisely executed throughout, with flush heads smoothly finished on all external surfaces. Panel gaps were minimal and consistent. Control surface hinges operated smoothly with proper lubrication and showed no signs of wear despite operational use. The attention to finishing details extended to components that pilots never saw. Internal structure was cleanly formed and carefully assembled. Wiring harnesses were neatly routed and properly secured. Hydraulic lines were correctly supported and protected from chafing. Even fasteners and small hardware showed consistent quality. This level of finish quality wasn't merely aesthetic. It reflected manufacturing discipline and quality control that ensured every component met specifications, that every assembly was completed correctly, that every aircraft leaving the production line met the standards necessary for the design to achieve its intended performance. German aircraft production in 1944 increasingly struggled to maintain such standards as Allied bombing disrupted supply chains, as skilled workers were conscripted or killed, as factories improvised with substitute materials and simplified manufacturing processes to maintain production numbers even as quality declined. The Mustang represented what was possible when manufacturing operated without these constraints, when quality could be maintained because the industrial system supporting production remained intact and adequately resourced. The cockpit layout and instrumentation revealed American attention to pilot workload management and ergonomics. Instruments were logically grouped and easy to read. Primary flight instruments were centered directly in front of the pilot. Engine instruments were positioned to the left, where they could be scanned quickly. Radio controls were accessible without requiring the pilot to look down or reach awkwardly. The gun sight was well positioned and provided a clear view. German fighters had functional cockpits, but instrumentation placement often reflected engineering convenience rather than pilot preference, and visibility was sometimes compromised by structural requirements. The Mustang's bubble canopy provided visibility that German pilots flying captured aircraft found remarkable. The pilot could see almost directly behind the aircraft by turning his head, eliminating the blind spot that characterized German fighter cockpits. This visibility advantage translated directly into tactical advantage because the pilot who saw his opponent first usually won the engagement. German pilots had learned through bitter experience that American fighters often spotted them first, got into advantageous positions before German pilots recognized the threat, and attacked from angles where German pilots' limited visibility prevented early detection. Flying captured Mustangs helped German test pilots understand why their operational pilots were being surprised so frequently despite years of combat experience. The maintenance accessibility impressed German ground crews who examined the aircraft. Inspection panels were large and positioned to provide good access to components requiring regular service. The engine could be removed and replaced using standard hoisting equipment, following clearly documented procedures. Major components were designed to be serviced or replaced in forward operating areas without requiring factory-level facilities. This attention to maintainability reflected American expectation that aircraft would operate from forward bases under field conditions, possibly under enemy air attack, maintained by mechanics who might be working at night or in adverse weather. German fighters were generally designed with the assumption that major maintenance would occur at established bases with proper facilities. Operating from improvised forward fields with limited support equipment was possible, but not the primary design case. The difference reflected broader philosophical approaches to military operations. American forces expected to operate offensively, establishing forward bases in recently captured territory, maintaining high operational tempo through efficient field maintenance. German forces designed for defensive operations, protecting the homeland, where established bases with proper facilities would be available. The radio installation in the captured Mustang demonstrated American progress in communication technology that had outpaced German development. The aircraft carried an SCR-522 command radio, providing clear, reliable communication over substantial distances. The clarity of transmission exceeded German radio capabilities, which suffered from persistent interference and limited range. German pilots flying captured Mustangs noted they could communicate more clearly with ground stations than they could in German fighters using Luftwaffe radios. This communications advantage provided American formations with better coordination, more effective tactical control, and superior situational awareness. Controllers could vector fighters toward threats or direct them away from superior enemy forces. Flight leaders could coordinate attacks with greater precision. Damaged aircraft could communicate their status and receive assistance more reliably. The cumulative advantage of superior communications was difficult to quantify in technical specifications, but was immediately obvious to anyone who experienced both systems in actual operations. By June of 1944, Rechlin had accumulated sufficient data from multiple captured Mustangs to compile comprehensive tactical recommendations for Luftwaffe fighter units. These recommendations were distributed throughout the fighter force, with appropriate classification markings. The essential advice was sobering. Engage Mustangs only when you possess significant advantage in numbers, altitude, or surprise. Never attempt to run from a Mustang in level flight because it will catch you. Never dive away from a Mustang because it dives faster than any German fighter. If you must engage, force the combat into sustained turning fights at medium altitude, where German fighters retain some advantage in turn rate, but be aware the Mustang pilot can always disengage by diving away, and you cannot prevent this. Avoid high-altitude combat entirely if possible, because Mustang performance dominates completely above 25,000 feet. The recommendations essentially advised German pilots to avoid combat with Mustangs except under ideal circumstances that were increasingly rare as American numerical superiority grew and tactical doctrine improved. The psychological impact of these recommendations on Luftwaffe fighter pilot morale was significant and measurable. German pilots had entered the war confident their aircraft were superior to enemy fighters, confident their training was better, confident their tactics were more refined. By mid-1944, official Luftwaffe tactical guidance was telling them to avoid combat with American fighters except under favorable conditions. The message was clear, even if unstated. German fighters were no longer competitive on equal terms. Survival required caution, selectivity, and acceptance that the Americans held initiative in deciding when and where combat occurred. Fighter pilots who had joined the Luftwaffe expecting to become knights of the air found themselves reduced to defensive reactions, scrambling to intercept bomber formations, hoping to strike quickly before escorts arrived, knowing they would be forced to disengage when American fighters appeared in strength. The transformation from offensive confidence to defensive desperation occurred gradually, but was complete by the summer of 1944. The strategic implications documented in Rechlin's technical reports extended beyond immediate tactical advice. German aviation engineers recognized they were examining an aircraft that represented a fundamentally different approach to fighter design, one enabled by industrial capabilities Germany no longer possessed. The Mustang succeeded through optimization and precision rather than through revolutionary technology. Every component was good, every system was reliable, every detail was properly executed. This comprehensive excellence required an industrial base that could maintain quality standards across thousands of suppliers, that could coordinate complex manufacturing operations across multiple facilities, that could implement engineering changes rapidly based on combat feedback, that could scale production to tens of thousands of units while maintaining tolerances measured in thousandths of an inch. Germany's industrial situation in 1944 made such comprehensive excellence impossible regardless of engineering skill or tactical need. Allied strategic bombing had degraded German manufacturing capacity systematically throughout 1943 and accelerating in early 1944. Precision attacks on ball-bearing factories, synthetic fuel plants, and transportation networks created cascading disruptions throughout German industry. Aircraft factories remained in operation, but increasingly struggled to obtain materials, components, and sub-assemblies from suppliers who were themselves struggling with damage, material shortages, and labor problems. Quality control deteriorated as inspection standards were relaxed to maintain production numbers. Skilled workers were conscripted for military service or killed in bombing raids, replaced by forced laborers who lacked training and often deliberately sabotaged production when possible. The cumulative effect was that German fighters produced in 1944 were often inferior in quality to those produced in 1942, even when they incorporated design improvements on paper. The North American aviation factory in Inglewood, California, that produced Mustangs operated without any of these constraints. The facility was never bombed, never damaged, never threatened. Skilled workers were available in adequate numbers, properly trained, and motivated by patriotism and good wages. Raw materials arrived on schedule without interruption. Component suppliers operated their own undamaged facilities with their own adequate workforces. Quality control could be maintained to specifications because maintaining quality didn't conflict with maintaining production numbers. Engineering improvements could be implemented systematically because the industrial system had capacity to absorb changes without disruption. By 1944, North American was producing Mustangs at a rate exceeding 400 aircraft per month, and every aircraft met specifications that German industry could no longer consistently achieve in any production quantity. The captured Mustangs at Rechlin demonstrated this industrial advantage with undeniable physical evidence. German engineers could measure it precisely, document it professionally, and report it accurately through their chain of command. The knowledge arrived far too late to influence Germany's strategic position. By the time comprehensive technical intelligence on the Mustang was compiled and distributed, Germany had already lost the air war over Europe. The question was no longer whether Germany could win, but how long Germany could continue fighting before inevitable defeat. The captured Mustangs eventually found their way into the Circus Rosarius demonstration unit, joining the collection of Allied aircraft that travelled to frontline Luftwaffe bases throughout occupied Europe. These demonstrations served purposes that extended beyond simple pilot education. German fighter pilots needed to see with their own eyes the aircraft they would face in combat, needed to understand the performance characteristics that made American fighters so difficult to counter, needed to accept the reality that their opponents possessed equipment advantages that individual skill and courage could not overcome. The demonstrations were carefully choreographed to show both the capabilities and the limitations of captured aircraft. German test pilots would fly the Mustang through various maneuvers, demonstrating its speed, climb rate, and handling characteristics. They would then fly German fighters through similar maneuvers for direct comparison. The demonstrations made certain truths undeniable. At high altitude, the Mustang was simply faster than anything Germany fielded. In a dive, it could not be caught. Its range allowed it to appear anywhere over Germany at any time, while German fighters were tethered to their bases by limited fuel capacity. Luftwaffe pilots who attended these demonstrations came away with mixed emotions. Some felt validation that their combat reports about American fighter performance had been accurate, that headquarters finally understood the capability gap they faced daily. Others experienced discouragement, recognizing that even when they executed tactics perfectly, flew their aircraft to the limits of performance, and demonstrated all the skill their training had provided, they remained at a disadvantage against an opponent who could choose to engage or disengage at will. The most experienced pilots often recognized the broader implications most clearly. Germany was not losing the air war because German pilots were inferior or because German tactics were flawed. Germany was losing because the industrial foundations supporting the Luftwaffe could not compete with the industrial foundations supporting the American and British air forces. Every damaged Mustang was replaced within days from production that exceeded 400 aircraft per month at peak output. Every lost American pilot was replaced by another adequately trained aviator from training programs that produced pilots in thousands. The logistics system supporting American operations delivered fuel, ammunition, and spare parts without apparent limit, while German logistics deteriorated under relentless air attack that the Luftwaffe no longer had strength to prevent. The technical intelligence gathered from captured Mustangs included details that revealed how quickly American aviation technology was advancing. Early Mustang variants had used Allison engines and showed good low-altitude performance, but struggled at high altitude. The decision to mate the Mustang airframe with the Merlin engine transformed the aircraft into a high-altitude performer that dominated the bombing altitudes over Germany. This wasn't simply an incremental improvement. It represented fundamental rethinking of the aircraft's role and capabilities, implemented rapidly through collaboration between American and British engineers. By the time German intelligence had fully analyzed the Merlin-powered Mustang's capabilities, American factories were already producing improved variants with bubble canopies that enhanced visibility even further, with increased ammunition capacity, with refined aerodynamics that pushed performance higher still. The pace of American development and the speed with which improvements reached operational units exceeded anything Germany could match in its deteriorating industrial situation. German attempts to develop fighters that could compete with the Mustang on equal terms founded on the same fundamental problems that affected all late-war German aviation programs. Promising designs existed on paper. Talented engineers understood what needed to be done. But translating designs into operational aircraft in meaningful quantities required industrial capacity, strategic materials, skilled labor, and time that Germany no longer possessed. The Focke-Wulf Tu-152 represented an attempt to create a high-altitude fighter that could compete with American escorts. It featured a more powerful engine, improved aerodynamics, and pressurized cockpit for better pilot performance at altitude. Small numbers entered service in early 1945, too late and too few to affect the strategic situation. The Messerschmitt Bf 109K variant incorporated numerous improvements to the basic design, attempting to extract more performance from the airframe. Production was limited and quality inconsistent. The jet-powered Messerschmitt Me 262 represented revolutionary technology that promised performance far exceeding any piston-engine fighter. But production numbers remained small due to engine reliability problems, fuel shortages, and Allied bombing of manufacturing facilities. Even when Me-262s reached operational units, pilot training was inadequate, fuel was scarce, and the logistical system supporting operations was collapsing. The Mustang, meanwhile, continued evolving. The P-51D model, with its bubble canopy and increased ammunition capacity, began reaching operational units in mid-1944. Performance improved marginally but significantly. The P-51H variant, developed late in the war, featured a more powerful engine and refined aerodynamics that pushed maximum speed above 480 miles per hour, making it one of the fastest piston-engine fighters ever produced. American industry implemented these improvements systematically, while simultaneously increasing production numbers, a combination that Germany found impossible to match. Quality remained consistently high even as production scaled because American factories operated with adequate resources, skilled workers, and undamaged facilities. The industrial advantage compounded over time. In 1942, German fighters were generally competitive with or superior to their Allied opponents. By 1943, the gap was closing. By 1944, American and British fighters had achieved parity or superiority in most categories. By 1945, the gap had become insurmountable. German pilots flew obsolescent aircraft in deteriorating condition against opponents with newer equipment maintained to higher standards and supported by logistics that functioned reliably. The fate of the specific captured Mustangs provides insight into the chaos of the war's final months. Charles Bailey's P-51, B serial number 43-6877, served with various evaluation units until it was eventually destroyed in an Allied bombing raid on a German airfield in early 1945. The aircraft never returned to American hands, its remains scrapped along with hundreds of other destroyed aircraft in the final collapse of German military resistance. Other captured Mustangs met similar fates, destroyed by bombing, sabotaged by their own former owners as Allied forces approached, or simply abandoned as German forces retreated and equipment was left behind. Few, if any, captured Mustangs survived the war intact. The pilots who flew them in German markings were test pilots and evaluation specialists rather than combat pilots, and most survived the war to provide detailed post-war debriefings about German aircraft development programs and technical intelligence operations. Charles Bailey's personal war ended more fortunately than many Allied pilots who landed in German territory. He spent the remainder of the conflict as a prisoner of war, primarily at Stalag Luft 1 near Bath on the Baltic coast. The camp housed Allied Air Force officers, and conditions, while harsh, were generally better than those in camps holding enlisted personnel or those operated by the SS rather than the Luftwaffe. Bailey was liberated by Soviet forces in May 1945 and returned to the United States shortly thereafter. His Mustang's contribution to German technical intelligence was significant but ultimately meaningless to the war's outcome. The knowledge German engineers gained from examining his aircraft documented the dimensions of their defeat, without providing any realistic means to avoid that defeat. Hans Werner Lersch, the test pilot who flew both the captured Thunderbolt and Mustang, survived the war with his remarkable safety record intact. His post-war memoirs provided detailed insights into German evaluation procedures and his personal impressions of Allied aircraft he flew. He noted that while he had flown superior German aircraft in certain specific categories, the Mustang represented the most complete fighter package he experienced during the war. It had no crippling weaknesses, performed well in every flight regime, and was clearly the product of sophisticated engineering supported by outstanding manufacturing quality. The broader lesson that emerges from the story of captured Mustangs in German hands centers on the relationship between design, philosophy, and industrial capability. The Mustang succeeded not through any single revolutionary technology, but through systematic optimization of every element of its design, pursued relentlessly, and implemented with precision manufacturing that maintained tight tolerances throughout mass production. This approach required an industrial base capable of consistent quality production at scale, something Germany possessed in 1939 but had lost by 1944. American aviation industry, in contrast, operated throughout the war with minimal disruption, adequate resources, and capacity to implement continuous improvements while simultaneously increasing production volume. The result was fighters that entered service good and got progressively better, produced in quantities that overwhelmed opposition through sheer numerical advantage even before quality advantages were considered. German aviation engineers understood these realities clearly by mid-1944. Technical reports compiled at Rechlin and distributed through Luftwaffe technical services documented American capabilities with professional thoroughness. The reports made clear that American fighters were superior in aggregate performance, even when German fighters showed advantages in isolated parameters. The reports explained why German pilots were losing combats despite individual skill and tactical competence. The reports quantified the industrial advantage supporting American operations and demonstrated why German production could not close the capability gap given resource constraints and ongoing disruption from strategic bombing. This knowledge was professionally gathered, carefully analyzed, and accurately reported. It was also strategically useless, because understanding the problem did not provide means to solve it. Germany needed aluminum, steel, rubber, fuel, skilled workers, undamaged, factories, and functioning transportation networks. Understanding that these resources were necessary did not make them available. The Mustang's impact on the air war over Europe extended beyond its impressive performance specifications. The aircraft enabled strategic bombing to continue despite German fighter defenses that had previously inflicted unsustainable losses on unescorted bomber formations. With Mustang escorts providing protection throughout missions deep into German territory, bomber formations could strike targets that were previously too heavily defended to attack effectively. The systematic destruction of German oil production, aircraft factories, and transportation networks became possible because escorts could protect bombers all the way to distant targets and back. This protection came not from Mustangs being invulnerable, but from them being present in sufficient numbers with adequate performance to make attacking bomber formations prohibitively costly for German fighters. Luftwaffe pilots faced impossible mathematics. They needed to destroy bombers to prevent damage to critical targets, but reaching the bombers required fighting through escort fighters that were faster, more numerous, and operating with fuel reserves that allowed extended combat, while German fighters were already near their range limits, just reaching the bomber formations. The strategic bombing campaign's success in destroying German industrial capacity created a self-reinforcing cycle that accelerated Germany's defeat. Bombing degraded German fighter production, reducing the number of interceptors available to defend against future raids. Reduced interceptor numbers meant more bombers reached their targets, inflicting more damage on industrial facilities. This additional damage further reduced production capacity, leading to even fewer interceptors available. The cycle continued until by early 1945, German fighter production had collapsed despite desperate efforts to disperse manufacturing and continue operations. The Mustang was the instrument that broke this cycle open. Its range and performance allowed bombers to reach any target in Germany with effective escort protection. Once escorts could protect bombers reliably, the systematic destruction of German war-making capacity became inevitable, constrained only by weather, target selection, and the time required to physically destroy widely dispersed industrial facilities. The human cost of this industrial warfare was staggering on all sides. Luftwaffe fighter pilot casualties reached catastrophic levels during 1944 as the qualitative and quantitative advantages shifted decisively against Germany. Experienced pilots who had survived years of combat died in unequal fights against superior opponents. New pilots with inadequate training lasted mere missions before being shot down. The Luftwaffe's training program collapsed under fuel shortages that limited flight hours for students and constant Allied attacks on training bases. Pilots reached operational units with perhaps 30 hours of flight time in type, facing American and British pilots with hundreds of hours of training. The predictable results filled casualty lists that German propaganda increasingly struggled to explain. American and British losses were also substantial in absolute numbers, but replacement pilots arrived regularly from training programs that continued operating efficiently in the United States, Canada, and Britain, far from combat zones. Every loss was tragic for the individuals involved and their families, but the military organizations absorbed losses and continued operations without degradation in capability. The technical intelligence program that captured Mustangs supported represented one of many areas where Germany invested significant effort that produced minimal strategic benefit. German intelligence services generally functioned effectively throughout the war, gathering accurate information about Allied capabilities, intentions, and operations. The problem was never that Germany lacked information about what they faced. The problem was that accurate intelligence about Allied superiority did not provide means to overcome that superiority. Knowing that American industry produced 5 times as many aircraft as German industry did not increase German production. Understanding that Allied fighters were superior to German equivalents did not make German fighters perform better. Recognizing that the strategic situation was deteriorating toward inevitable defeat did not create options for avoiding defeat. Intelligence can inform decisions, but it cannot create options that do not exist due to fundamental resource and capability limitations. The story of German engineers testing captured Mustangs ultimately becomes a story about the limits of tactical excellence when facing strategic disadvantage. German aviation engineering was sophisticated, German pilots were skilled, but these advantages could not overcome the industrial mathematics that governed modern warfare by 1944. The United States produced more aircraft, trained more pilots, generated more fuel, manufactured more ammunition, and sustained operations at intensity levels Germany could not match. Britain and the Soviet Union added their own substantial production and combat power to the equation. The combined Allied advantage was overwhelming, and it grew larger over time rather than smaller, as American industry continued expanding production while German industry contracted under bombing and resource exhaustion. The Mustang was both symbol and instrument of this advantage. An excellent fighter aircraft produced in quantities sufficient to establish air superiority over Germany itself, the final step before inevitable ground defeat. Up next, you've got two more standout stories right on your screen. If this one hit the mark, you won't want to pass. These up. Just click and check them out. And don't forget to subscribe and turn on the notification bell so you don't miss any upload from us.